Hello everyone, welcome to lecture 29 in the course Diffusion in Solids. Last class we defined what are known as the intrinsic diffusivities. We looked at what is known as the Kirkendall effect, and we defined it in more qualitative terms, how it led to the the acceptance of the vacancy mechanism for the diffusion. Today, what we will do is we will try to see that quantitative analysis, so that we can have some expression for intrinsic diffusivities and how they are related to interdiffusion coefficient. Remember, in the Kirkendall experiment, he only showed that the Marcus movement is there, which gave the important insight that the diffusivities are not equal. But there was no mathematical analysis of the process. That was done later by Darkens. So, just before we step on to the Darkens analysis, there is one small relation I want to convey, which is for what are known as partial molar quantities. So, for example, we know this chemical potential. Chemical potential is nothing but dou G bar by dou Na at constant temperature, pressure and Nb if it is a binary solid solution, and which is also can be expressed as Ga bar equal to mu A. What it means is partial molar quantities are that if I add a small amount of A, how much the overall quantity or the property changes. In this case, for the chemical potential, it is the free energy. So, if I add a small amount of A, how much the free energy of the solution changes. Similarly, you can define partial molar quantities anything. For example, you have Va bar, which is the volume, that is equal to dou V by dou Na at constant temperature, pressure and Nb. Similarly, Vb bar also. So, the overall total volume can be written as Va bar into Na plus Vb bar into Nb. That means partial molar volume of A multiplied by the number of moles of A plus partial molar volume of B multiplied by number of moles of B. Now, if I divide this expression both sides by Na plus Nb, V by Na plus Nb, that means the total volume divided by the total number of moles in the system is my molar volume, which is Vm, and here Na by Na plus Nb becomes Xa, this becomes Xb. So, we have Vm is equal to Va bar into Xa plus Vb bar into Xb. Now, Xa can also be written as Ca into Vm. See, Ca is nothing but moles per unit volume, okay, and the partial molar volume is volume divided by the total number of moles. So, that is equal to the mole fraction. Now, Vm therefore can be written as Va bar into Ca into Vm plus Vb bar into Cb into Vm. So, this Vm, if you cancel on both the sides, what you get is Va bar into Ca plus Vb bar into Cb is equal to 1. We will use that expression very soon. So, what Darkens analysis, how he approached. See, basically, if you consider this as a diffusion couple, and where after initially you placed a marker plane, these black dots indicate the position of the markers, and after a time t1, this movement of marker happens to this distance. After a time t2, the movement of markers happen to this distance, and so on. Now, can we quantify this? So, what he tried to do is, by the way, this is a question for you, which is the faster moving species here. I have indicated Xb minus and Xb plus, which means that it is lean in B, it is more in B here. So, the other element is of course A. So, you have to try to guess which the diffusion is faster, from right to left or from left to right. Now, as I said that from the Kirkendall's experiment, it was clear that one diffusion coefficient is not sufficient, you need to determine 2. So, the interdiffusion coefficient is measured with respect to the initial contact plane, which is x0, which is also known as the metallic metanoplane. However, the intrinsic diffusion coefficient should be only measured by the continuously moving the marker plane, xk, because marker plane measures the relative movement of the flux of species A and B. Okay. So, the movement of marker actually indicates how is the relative motion between A and B. So, therefore, any intrinsic diffusion coefficient determination should happen only at the Kirkendall marker plane. So, if we want to write using the Fick's first law for the intrinsic flux and the intrinsic diffusion coefficients at the marker plane, we can write JA is equal to minus dA dou CA by dou X at Kirkendall marker plane. Similarly, we can write the flux of B is equal to minus dB into dou CA by dou X at the Kirkendall marker plane. Now, what Darkens developed is the relation between the interdiffusion and intrinsic fluxes. So, what was written is that JA tilde, that means it is the interdiffusion flux for A, is equal to JA plus Vk into Ca. That means Vk is the velocity of the Kirkendall marker plane here, and Ca is the composition. So, you see that it is like adding a drift term to your intrinsic flux, which gives you the interdiffusion flux. So, this interdiffusion coefficient, if you try to draw an analogy to the relative velocity concepts that you have studied in high school or higher secondary, the thing is this is like that. So, when JA tilde you write, you are talking about the laboratory frame of reference, whereas when you write JA, that is the intrinsic flux which is measured at the Kirkendall marker plane, it is the lattice frame of reference. So, this JB tilde is written as JB plus Vk into Cb. Now, if you utilize the Boltzmann variable, you can write lambda is equal to xk minus x naught by root t. Remember again that we are working on at the Kirkendall marker plane. Since x naught is our origin, we can simply write this as xk by root t. So, if I take the differential of this, velocity is equal to dxk by dt, which will yield xk by 2t, because I can write xk as lambda into root t divided by dt, and this will give me Vk is equal to xk by 2t. What do I do then? So, as I said, this velocity can be calculated by using the above method. That means, xk you can measure by using your microscope and so on. You can measure the distance, how much the Kirkendall markers have moved, and you know the time of annealing. So, you can determine the velocity of the Kirkendall marker plane. Now, the interdiffusion flux can be written as minus d tilde into dou Ca by dou X. What we have seen before, Va bar into Ca plus Vb bar into Cb is equal to 1. If you differentiate this, what you get is dCa is equal to minus Vb bar by Va into dCb. So, if you substitute this here from the 1 and 2, you get Ja bar is equal to minus d tilde into minus Vb bar by Va bar into dou Cb by dou X. And if you take Vb bar by Va out and d tilde inside, this d tilde into dou Cb by dou X including minus becomes Jb bar. So, what it tells us is that the Ja bar, Ja tilde into Va bar plus Jb tilde into Vb bar is equal to 0. So, if I now substitute Ja bar as Ja plus Vk into Ca, similarly Jb plus Vk into Cb here, what I get is something like this. Here, that means if I rearrange, I take these terms Ja into Va bar plus Vk inside the bracket, I have Ca into Va bar plus Cb into Vb bar. Now, we showed earlier in the couple of slides back that this quantity is equal to 1. So, therefore, you can have Ja into Va bar plus Jb into Vb bar plus Vk is equal to 0. So Vk can be written as minus Ja into Va bar minus Jb into Vb bar. Now, if I again utilize this expression Jb tilde is equal to Jb plus Vk into Cb, I can do this minus d tilde dou Cb by dou x at Kirkendall marker plane is equal to, this is the intrinsic flux, remember, that minus dB into dou Cb by dou x again at the Kirkendall marker plane, and I can substitute this expression for Vk as minus J into Va bar minus Jb into Vb bar into Cb. So now, what I need to do is if I just substitute the value of Ja as dA into dou Ca by dou x at k, because there is already also minus that comes into picture, so this minus goes off, plus dB into Vb bar into dou Cb by dou x at k into Cb. Now, what you also saw from the equation 2, that means this was the equation that was presented here, this one, so that I can interchange or I can replace dou Cb or dou Ca, one of them. And so the dou Ca by dou x is nothing but minus Vb bar by Va bar into dou Cb by dou x. So if I substitute it back here, what I get is minus d tilde into dou Cb by dou x is equal to minus dB into dou Cb by dou x at Kirkendall marker plane plus inside the bracket, see these terms carefully that you have dA here, but because there is a relation between the dou Cb by dou x and dou Ca by dou x, we can write here minus Vb bar into dou Cb by dou x plus dB into Vb bar into dou Cb by dou x overall multiplied by Cb. So now, because this Vb bar into dou Cb by dou x at the Kirkendall marker plane is common, what you get is dB minus dA as the bracket term, and therefore, you can have this expression now written in this way. Now, dou Cb by dou x is common here, so it get cancelled. What you end up is in minus d tilde is equal to minus dB plus dB minus dA into Vb bar into Cb. Now, if you take the dB terms common, that means the dB minus dB if you take common, then you get 1 minus Vb bar into Cb minus dA into Va bar into Cb. Now, this minus you can remove from both the sides. So, you get d tilde is equal to dB multiplied by, remember 1 minus Vb bar into Cb is nothing but Va bar into Ca. That is why we wrote this relation the very first slide of this lecture, because there is multiple times so we have used it, plus dA into Vb bar into Cb. So, if we assume that Va bar and Vb bar are equal and are equal to the partial molar volume, then we use Xa is equal to Vm into Ca and Xb is equal to Vm into Cb. We get this equation, which is d tilde is equal to Xa into dB plus Xb into dA. So, this is what is known as the Darkens equation. Obviously, if you see that as Xa tends to 1, that means predominantly if it is A, then actually the interdiffusion coefficient is more influenced, or it is almost equal to the diffusivity of the B, intrinsic diffusivity of B at vice versa. Remember this expression again, especially when you are solving the assignments or tutorials and in exam. Remember this expression is d tilde is equal to Xa dB plus Xb dA. Do not make the mistake of writing it as Xa dA plus Xb dB. It is Xa into dB plus Xb into dA. So, you remember that. I want to introduce one more quantity today to you, which is known as the atomic mobility. See, when we define the diffusion coefficient, it is when we talk in context of the Fick's law. That means you are relating the flux to the concentration gradient, and the constant is the diffusivity. But we also saw that actually it is the chemical potential gradients that drive the diffusion process. So, we have to have some quantity which is representative of that. So, in one of the previous classes, we have seen this relation that I just mentioned, that Ji is equal to summation 1 to n minus Lij into dou mu j by dou x, which is known as the Onsager's relation, which basically relates flux to the chemical potential gradient. And we can write Ja for a binary system as minus Laa into dou mu a by dou x minus Lab into dou mu b by dou x. Now, if you assume that the vacancy equilibrium is attained instantly, then Ja is equal to minus La into dou mu a by dou x. Okay. Before I go to further, just remember that when we derived the Darkens relation, we considered only the flux of A and B. We did not consider a vacancy flux, although I had indicated this in the previous lecture. So, the reason is that in the Darkens analysis, he assumed that the vacancies come to equilibrium instantly. Okay. So, there is the establishment of the local equilibrium instantly, and based on that the Darkens relations were derived. So, now here we have written Ja is equal to minus La into dou mu a by dou x. See, you can express flux in another way also, which is Ja is equal to Ca into Va, where Va is the mean velocity of A atoms. You can check the dimensions, it will match out also, and you will see for yourself that it makes perfect sense that the flux can be written as the velocity into the concentration per unit volume, or the number of moles per unit volume. So, also the velocity is proportional to the driving force. This is the basic principle which is usually applicable, that velocity is proportional to the driving force, and if you see then that Va is equal to some constant into the driving force, and this constant is known as the mobility of A. So, if I write Va, which is the mean velocity of atoms, is equal to minus Ma into dou mu A by dou x, which is the driving force. So, this Ma is what is known as the mobility of A. You can also express it as the velocity per unit driving force. So, therefore, we can write Ja is equal to minus Ma into Ca into dou mu A by dou x. Okay. So, you see that here I had written Ja is equal to La into dou mu A by dou x, and I can now write Ja because I am writing here minus Ma into Ca into dou mu A by dou x. So, if you compare this 3 and 4, this expression here and this expression here, then you can write La is equal to Ma into Ca, and which can be written as La is equal to dA star by RT. So, the mobility term is actually equal to the dA star by RT. Here A dA star means the tracer diffusion coefficient. So, this relation, how this La is written as dA star into Ca by RT, it has a separate derivation of its own, and it is beyond the scope of this course, but you are free to get into some extra reading and try to see how it is derived. You can refer to one of the other NPTEL lectures on the diffusion, on the multi-component diffusion in solids, where you will find the derivation for this relation. So, this mobility is equal to dA star by RT. Okay. Now, in the Darkens relation, what we talked about is the intrinsic diffusion coefficient and the interdiffusion coefficient. There is another interesting quantity that we'll define, or we'll also try to see quantitatively, which is known as the thermodynamic factor. What actually this thermodynamic factor is? So, basically thermodynamic factor comes into picture when you are trying to relate this mobility to the intrinsic diffusivity dA. Okay. So, we have written here MA is equal to dA star by RT. That means the mobility is to the tracer diffusion coefficient. But how this mobility is related to the intrinsic diffusion coefficient? So, for that, it's a little bit of thermodynamics today, but don't worry, I am giving you all the relevant equations. You can also go back and read further. So, the chemical potential can be expressed as mu A naught plus RT ln AA, which is the activity of A. If you differentiate, dou mu A by dou XA is equal to RT dou ln AA by dou XA. That is, let us say we call it as equation number 5. Now, remember in the equations previously, when you are relating flux, you have dou mu A by dou small x. See the difference here, this is XA, which is the mole fraction. This x, small x, is the distance. So, using the chain rule of differentiation, I can write this as dou mu A by dou Ca into dou Ca by dou x. Now, we know that Ca is nothing but Xa by Vm. So, I can replace this Ca here, and from 5 and 6 equation, what we get is dou mu A by dou x is equal to Vm into RT into dou ln AA by dou Xa into dou Ca by dou x. Okay. So, this is how we can write. Moving ahead, how is the activity defined? Activity is nothing but the activity coefficient gamma into the mole fraction of A. So, which is AA is equal to gamma A into Xa. So, if I calculate dou ln A by dou Xa, I will get dou ln gamma A by dou Xa plus 1 by Xa. Remember, differentiation of log Xa with respect to Xa will be 1 over Xa. So, I can substitute this expression here, and what I get is dou mu A by dou x is equal to Vm into RT 1 by Xa plus dou ln gamma A by dou Xa into dou Ca by dou x. This activity coefficient can have the value 1, greater than 1, or less than 1, depending upon the type of the solid solution. It is equal to 1 if it is a ideal solid solution, in which case A is equal to Xa. Now, you get this expression. So, if you see from the equation number 7 and the equation number 4, okay, where you had in the equation number 4, if you see, you had J is equal to minus Ma into Ca into dou mu A by dou x. So, I replace this dou mu A by dou x here, and what I get is J is equal to minus Ma into Ca into Vm into RT into 1 by Xa plus dou ln gamma A by dou Xa into dou Ca by dou x. Now, this Ca into Vm is nothing but Xa. So, I can write J is equal to minus Ma into Xa into RT 1 by Xa plus dou ln gamma A by dou Xa into dou Ca by dou x. Now, if I take this Xa inside, what I get is 1 plus dou ln gamma A by dou Xa by Xa into dou Ca by dou x. Now, this dou Xa by Xa can be written as dou ln Xa. So, I can have this expression alternatively like this. Now, compare this expression. So, you see that this is the whole quantity multiplied by dou Ca by dou x. So, what is this quantity? This is nothing but the compare with J is equal to minus dA into dou Ca by dou x. So, the dA is actually equal to Ma into RT 1 plus dou ln gamma A by dou Xa. So, this dA is equal to this. Now, this dA is equal to Ma into RT into phi, where phi is equal to this quantity. This quantity is what is known as the thermodynamic factor. Okay, and we saw that MA into RT is nothing but dA star, which is the tracer diffusion coefficient. Therefore, you have dA is equal to dA star into phi. So, this phi is equal to 1 plus dou ln gamma A by dou ln XA. It is called the thermodynamic factor. Now, if you substitute this dA as dA star into phi in the Darkens equation, what you get is d tilde is equal to xp into dA star plus xa into dB star into phi. So, this is the Darkens equation in terms of the tracer diffusion coefficients. The last thing for today's lecture is something called as a vacancy wind effect. See, I told you that the Darkens equations are obtained if the concentration of vacancies are in thermal equilibrium during this process. So, that means the vacancy equilibrium is attained almost instantly. However, for the Kirkendall effect to occur, vacancies must be created at one side, annihilated on the other side, so that a vacancy flux is created. So, that means how these vacancies will be annihilated? Only if there are enough sources and sinks present in the diffusion couple. So, if the number of sources or sinks are not sufficient, then you have a net vacancy flux, which causes what are known as a vacancy wind effect. That is a correction term that must be added to the original Darkens equations, and this was suggested by Manning. So, you have something called as Darken-Manning relations. So, basically you say that dA is equal to dA star, instead of dA is equal to dA star into phi, what we write it as dA is equal to dA star into Vm by Vb bar into Ra. So, this Ra is the vacancy wind factor for the diffusion of the A. Similarly, for B, it is equal to dB star into Vm by Va bar into Rb. So, Manning suggested to use a factor which is an overall vacancy wind factor S, which is equal to Xa into dB star into Rb plus Xb into dA star into Ra divided by Xa into dB star plus Xb into dA star. So, with the vacancy wind factor, the equations is modified to what is known as the Darkens-Manning equation, which is d tilde is equal to Xa into dB star plus Xb into dA star into phi into S. So, this S is the correction term for the vacancy wind effect. So, with this we have closed the interdiffusion analysis portion, and in the next week we will see some of the computational tools that we can utilize to predict the diffusion profiles and so on. So, that is the computational aspects I want to give a brief intro to. So, that we will do in the next week. So, but for the next lecture, of course, we will solve certain problems as the tutorial lecture. So, thank you, and see you for the next lecture.